what is the surface plasmon resonance, what these plasmonic nanoparticles are, and what are the processes that they undergo as they are excited and then decay back. In that context, if you remember, I had talked about the mean free path, the electron scattering, electron phonon scattering. So these are events that really determine whether this plasmon will be a dominant one, the absorption will be very strong or very narrow or broad. So all these things depends on somewhere on these factors. Okay. So now moving further, so these are the basics that we had discussed regarding the plasmon frequency. So SPR frequency can be, yes, it is defined for the bulk is defined as this n e square. So you can see this all these thing in the under root n e square epsilon naught me. So the two variables here are the n capital N and the me. So me and n. Rest of the things are constant. So when the metal is placed as at the interface in vacuum, these are the two factors that will affect the plasmon resonance, electron density, and the mass of effective mass of the electron. Bulk plasmon frequency as depends only. So you can say that yes, effective mass also changes from metal to metal, but it's the electron density which is mainly affecting it as far as this equation is concerned. So we found that it can be this. It was also discussed yesterday that all the metals have certain plasmon frequency. We can think of the collective oscillation of electrons on the surface, but most of them have their this plasmon frequency located in the ultraviolet spectrum, ultraviolet region. Okay, it is only the copper, silver, gold that exhibit plasmon frequencies in the visible region, and that's why we usually call them as plasmonic nanomaterials. So something that is stable at room temperature, that exhibits peculiar plasmon frequencies in the visible region. So all these things makes up. Okay, so silver and gold are the most common one. Even copper is also used as has been shown to be having plasmon frequency which is stable at room temperature, but it's also there's a problem that it gets oxidized or something, oxidized, or then the plasmon frequency will be vanished after some time. It is only silver and gold which will remain stable if you make nanoparticles and put it in the solution phase. That is the colloidal. If you make a colloidal solution of silver and gold, they will stay for a longer time. They are very stable. Okay, and particularly gold is also non-toxic and suitable for biological application. Even still, silver is slightly toxic, but with proper surface modification, we attach certain organic moieties on the surface, which is biologically compatible, and then it turns out that it is even better than the gold when we use it for therapeutic or diagnostic purposes. So the range of this thing, SPR peaks can range. It can go from 650 to 1200 nanometer. So it is the requirement for biological application. We require that it is tuned into this range, somewhere between, because the blood uh, absorbs in the visible region. It is red in color. There are also other cellular components which will tend to absorb when you are working in the visible region, and that may not be a good thing, because there will be unwanted photo damage to the healthy cells. So we need to take care of that. and it has been found that it is this window between 650 to 1200 which is found to be the spectral region where the biological components do not absorb light, or their absorption is very very less, so that it is not going to affect. So normally what happens that whenever these silver or gold nanoparticles are used for this therapeutic purposes, it is they we have a trigger in form of laser light which is used. So it is useful if you have even a visible laser would be damaging to the healthy cells if it is absorbed by them. So we have to find a area in the a region in the spectral electromagnetic spectrum where no cell components, none of the cell components, none of the biological components, or cell organelle, blood, anything does not they do not absorb in a particular area. That will be the most suitable one. It will not cause unwanted side effects, will be less, unwanted damage will be less to the healthy cells, and only the cancer cells or disease cells where the nanoparticles are localized, only that will be affected. So that's, we call it a biological transparent window. Then this one. So it so happens, yeah, as I told you yesterday also, the surface electrons only which will be affected, and so you don't have to consider, although electrons are delocalized over throughout the crystal lattice, the penetration depth of electromagnetic wave is less, up to few nanometers, and so you can consider the effect is limited to the surface electron, and that's why the term surface plasmon. So propagating and LSPR, so this is also was discussed. Remember that. So propagation means moving in a certain direction. So that's how you see that this is moving. This oscillation is looks like that electrons are moving in a particular direction. Whereas in this one, it is this, at the same place. It is like a standing wave. So in this case, it is a standing wave, and in this case, in the top one, the propagating SPR, it is behaving as a traveling waves. Okay, so now we should understand what are the factors that affect this SPR, surface plasmon resonance. So it is the size of the nanoparticle, shape, structure, all these things. So it is the very inherent nature of the nanoparticle, which can affect surroundings, the capping agent, the dielectric constant of the medium. So this is also going to affect it. So the size factor, if I tell you, this is the range. So gold, the best known plasmonic nanoparticle. If I talk about it, a typical 10 nanometer of size will be having absorption around 520 nanometers. So it looks almost red colored. And then as you increase the size from 10, 22 nanometer, 48 nanometer to 100 nanometers, you find that the maximum change that we can obtain is around 580 nanometers. So that's the how the absorption peak changes, the colors change. So it is a function of the size of the nanoparticle. So that's what clearly reflected, but the change is very small. It is about 60 nanometer change. By we have covered the entire range up to 100 nanometers of the size, but there's no further change in the beyond 580 nanometers. So it is still, we are still in the visible region. But as I told you, for applications, for biomedical application, it is essential that we move to the near IR region, that is the 650 to 1200 nanometers. But so how is it possible to achieve? We don't know. We have to So you'll just see in the next few slides how can we achieve that. So similarly, if you analyze this spherical nanoparticles of silver and change the size from 5 nanometer to 100 nanometers, you can see it is having from 390 nanometers to 460 nanometer only. So there is around 70 nanometer change in the absorption peak. Okay, so this is something that is so as the size increases, we are having a clear change, but the change is not sufficient enough for uh, in the sense that yeah, we are not reaching the biologically transparent windows 800 nanometers and beyond, 650 nanometers and beyond. So size, just changing the size doesn't have much effect. It has an effect on the plasma on resonances, but that is very small, around 60 to you we just saw that 60 nano, it was the up to 100 nano. So starting from 10 nanometers to 100 nanometers, the range that we are getting in case of gold is 60 nanometer change in the absorption peak, whereas in case of silver we are obtaining around 70 nanometer change. So that's a very small one, and you are still stuck in the visible region. Now if you want to go to the near IR region, clearly, so you need to change the shape. If you change the shape, such as if instead of spherical nanoparticle you make it in form of rod, then the plasmon resonance splits into two modes. So there could be oscillations along this positive, negative, or along this. So transverse axis, longitudinal, and so longitudinal SPR and transverse SPR. These are the two ways in which you can have this kind of thing. Okay, so transverse surface plasmon resonance, transverse SPR, longitudinal SPR. So these are two modes that we can think of. The way I told you, the dipole can develop either oscillation can have electrons, collective oscillation of electron can happen along this axis or along this axis. So it is the longitudinal SPR which is tunable. The cross-sectional area that you see in a rod, uh, that will have a fixed value around 500 something in gold, but the longitudinal SPR goes on, can be tuned. So you can see here it is more than 800 nanometers, or so 820 nanometers or something like that. So now we are able to get the plasmon frequency in the near IR region, which is more suitable for biomedical applications. Okay, and here in the near IR region there is also enhanced photothermal effect, that light to heat conversion, and the treatment efficiency for the cancers is enhanced. Okay, so the shapes, the narrow rods, the nano plates, uh, you can see these are the things that is so the variation. So it is, there's something called aspect ratio. So this is what you see here written over here. So it is the function of aspect ratio that we can, if you want to define that, what is the, how is it possible to change, tune this plasmon frequency starting from 800 to around 1100 nanometers. It is possible by changing the aspect ratio. We call it aspect ratio. AR stands for aspect ratio, which is the length, major axis, or you can say the by minor axis, you can say something like that, or the length by the diameter, or you can say the, if you are talking of rod, then you have this length by diameter. So you can say length by diameter is the thing that we call as aspect ratio. So if this aspect ratio changes, so as the aspect ratio increases from 2.4, 2.9, 3.5, 4, 6, up to 6.6, there is a change, shift towards the red, near IR region. Okay, so we can clearly see this electron cloud and this. Okay, so these are the factors that affect the SPR wavelength. So now if you talk about, we talk about this, so these are the, so different shapes. So the changing the shape has a major effect. So far what we learned from this is that the size is not that important. Simple keeping a spherical shape and changing the size doesn't change the uh, plasmon frequency wavelength much. You got only 60 or 70 nanometers change, but now you can see that you have 600 to 1000 nanometers. So there's a huge 400 500 nanometer tunability range that you have got. So nanoplates, nanorods, you can, in all of them you can define the aspect ratio, and it is the change in the aspect ratio that gives you, so that gives rise to this kind of tunability, the change tunability of SPR wavelength. So the SPR wavelength is very sensitive to the aspect ratio of the anisotropic structure. These are called anisotropic structures, where the one axis is different from the other, and spherical one is isotropic. You can say that in all the directions it has same length. Okay, so this is an example where on this slide, a sphere of 40 nanometers, a cube of 14 nanometer. Right? So this is how the plasmon frequency changes. Tetrahedron. So this is the pattern in which, so change in shape will have definitely a very big effect on the plasmon frequency. And so this is the kind of thing that we have also obtained in our lab, something like this. So we have been also able to change the shapes from pyramidal to like structures. Spherical one is yellow in color, and so this is spherical, and then this is like plate and these are all, these are pentagonal pyramids type. So in this case, so all of these have different dimensions. The edge length of the pyramid is different, and so you get different kind of nanoplates, nanopyramids. And then there is also one thing, that is the internal structure of the nanoparticles. If you inside is make hollow, or you keep the shape as spherical but make it hollow from inside, then also there is change in the plasmon frequency, the SPR frequency changes. So the first one is the spherical uh, nanoparticle, say a gold nanoparticle. Then if we make this hollow from inside, okay, then in this this is the void space that we call it as void space. Void space becomes bigger gradually, and the plasma, so what you find is that becomes bigger. So gradually you will see, as you make this void space bigger inside this, keeping the outer diameter same, then there will be, so we are making a nano shell. If taking a spherical one, if you make hollow from inside, it is a shell, and the shell, the void space is max as you make. So thickness of the shell is, so this is the shell thickness that we can define. Shell thickness. So this is a thinner shell, thinner shell, and this is a thicker shell. So now if you try to put it, so hollow, when you try to do this, make it hollow, then what happens is that, as I told you, okay, so hollowing out of the nanosphere, the aspect ratio changes, outer diameter to shell thickness. This is the ratio that is important. Redshift of the plasma on peak, and this is quite evident in gold nanoparticles from 550 nanometers to 820 nanometers. Okay, so you can see here how the these colors are changing as you change the frequency. Sorry, it is the last one is, I'm taking it wrong way. 550 is this one, and 820 is this one, like this. So you have a starting from the visible range, the red color, you are moving to the near IR range. 820 nanometer is represented, is a near IR level that we are talking about. So by keeping, so even if you keep the size shape as sphere, nanosphere, make it hollow from inside, so internal structure changes and the SPR frequency moves to the near IR wavelength. So that's a huge tunability that we can obtain, 500 to so almost 300 nanometer change. So which we were not able to do when the size was spherical, solid from inside, there was no void space. You make it bigger from 10 to 100 millimeter, and there was no such tunability was there. Only 60 nanometer change was observed, right, in the gold. So the reason for this remarkable tunability by in the nanoshells is assigned to this what we call is the theory that has been developed. It is similar to what you have learned already in the molecular orbital theory. So it is nanoshell can be considered to be a superimposition of a sphere and a cavity. So you have extended a sphere of particular size, and you also have a extended network of gold, and in which you make a hole. So that cavity you make, and then superimpose these two structures, you get the nanoshell. Okay, so in the nanoshell there are two surfaces, one on the top, one the outer surface, one is the inner surface. So what we see in this scheme, that there is hybridization of there are two surface plasmon resonance mode, inner surface, outer surface, and both of them are getting hybridized to give you symmetric and anti-symmetric dipoles. So you can see here, so this is a lower energy and this is higher energy. So there is a small peak that would have been appearing over here. You can see around 400, so anti-symmetric. And all these change tunability that you are seeing is the symmetric dipole. These are all symmetric dipole that is being tuned. And the small rise that you see towards this 400 nanometers, that is the what we call as antisymmetric dipoles, the small intensity. So it is also important. So, so both of these have been observed. So it is the interaction between the two plasmon resonance modes to give you a composite one single appearance over here. Hybridization occurs with plasmon solid sphere, and this is how it happens. Okay, so nanoshell, symmetric mode, both are in phase. The outer dipole, inner dipole, both are in phase, and that is symmetric dipole. This is symmetric because both dipoles in phase, in the same phase. Here antisymmetric because both the dipoles, this is antisymmetric, out of phase. Okay, so these are the things that will affect. And there's also an important thing that we should note is that it is the extinction. In the earlier cases, it is a very old theory, me theory, which is so E here is the extinction, and you should know that in such nanostructures, nanoparticles, there will be significant scattering that will take place. So to account for, so it is a, what is this extinction that we are talking about? This is a term that will be extinction. So this is what we call extinction. Extinction is a term that is it is taking into account of absorption plus scattering. In simple small molecules, the scattering is very less, and we can ignore it. But in case of uh, so scattering is a term that is always there, but insignificant, significant in small molecules, significant in large, significant for, but it will be very high in case of colloidal, significant for colloidal solution of nanoparticles. Okay, but this, so rather it should not be given like this. It is a different aspect. So it is significant, and it will be substantially high for nanoparticles of larger dimension, larger size. Okay, so when you have around 100 nanometer particle, the scattering would be more. 50 nanoparticle, there will be scattering, but it will be less. And when we are talking about molecules which are of few angstroms, it will be insignificant. So scattering is dependent on the size of the species that falls in the path of light. Absorption is something that depends only on this thing. So what you must have seen that we always talk of molar extinction coefficient. So extinction is the more fundamental term. That's why it is not called molar absorption coefficient. It is always called molar. It is for the same precise reason that it is we call it molar extinction coefficient. It takes into account both the absorption and scattering. Okay, so when if you can see it this way also, when you have something in the path of light in the spectrophotometer, when you put something in the path of light, there are two things that can happen: absorption and scattering. Both can happen. And so if I can put it like this, you have something. Okay, you have light source. So as it reaches over here, beam of light that is traveling, some of them might be get scattered, some of them might pass through, and the other may just be absorbed and reach the detector. So detector only notes the photons that is reaching it, the wave that is reaching it. So if you have a monochromatic light source, so the detector will see that only out of 4 photons, only one has reached it. Okay, in this particular example, and one of them was it doesn't know, so it will only so this you see in the spectrum you get plot of absorbance A versus lambda. So A at that particular level, so it notes it, so you it is minus log of I by I naught. So it takes the intensity that was without sample and with the sample. Okay, so what is happening here, detector only notes that without sample there was certain number of photons, 100 photons were coming. Now after uh, when the sample has been put in the path of light, there are only 40% photons that is reaching it. So that means rest of the 60 photons have been absorbed. That's what detector sees, and it calculates uh, and it plots a, and you get a plot like this. So it is counted as absorption. In fact, it is this absorption that you have thought of. In case of nanoparticles, what happens, it could be absorption, but there is also significant amount of scattered radiation which has not reached the detector. So ये जो detector के पास scattered radiation जो नहीं पहुंचा है वो भी तो absorbance में count हो गया है. So the true picture would be to say, so we say that it is the extinction which is a fundamental point, and the photon traveled from the light source and it got extinct, वो गायब हो गया. जो डिटेक्टर के पास पहुंचा, आपने रेशियो लिया दोनों का और आपने कहा कि ये हमारा एब्जॉर्बेंस है. दैट इज ट्रू when you have a small molecule or very small very small molecules or complex that is a few angstroms in size. But when you have particles of 10 nanometer, 100 nanometers, 50 to 100 nanometers, there will be significant component of scattered radiations which will not reaching the detector. And by the algorithm is like that it will take into account all those that is not reaching the detector as absorption. But now you know that there is contribution of both absorption and scattering, which is on screen you get as absorbance, right? So it is a more fundamental term. Scattering and absorption both happen simultaneously, but it is in case of nanoparticles or something, scattering cannot be ignored, and it is better to represent it with extinction, right? So this is combining. So what you see here is that, so to be more scientific in your explanation, and this we take both things into account, the scattering and absorption. So this extinction of these surfaces, that metallic surface that we are talking about, it will depend on the it also depends on the interface that it has with the surroundings. And so you can see that the terms here are coming over here is this epsilon m. This is the medium, dielectric constant of medium, constant of medium. And epsilon r is the real part of the real part. It is the dielectric constant of the metal, constant of metal, the real part. So it will have two components, the real and imaginary. So the real part of the function. And then you have another one which is epsilon I. This is the dielectric constant of the medium, dielectric constant of the metal. This is the imaginary part. Okay, so imaginary part. So it is a combination of these things that will define the surface plasmon resonance. Okay, rest of the things you have mean free path. It is the wavelength lambda, the size, the r that you are seeing. All these things are there, and the composite epsilon. So if you look at it carefully, so the condition for resonance is that from this equation, resonance condition is achieved when epsilon r is equal to the real part of the metal's dielectric constant is equal to this. So what happens? This term will go to 0. Under this condition, when this happens, the term, this will be 0. And you are left with epsilon I square by this. So this is resonance. So this is essential condition for resonance to be odd when you change the solvent. And because of this reason, when you change the solvent, the medium changes, and then the condition for resonance has changed, and you will have achieve the resonant condition will be achieved at a different frequencies. So SPR frequency also shifts because of the change in the medium's refractive dielectric constant. So oscillating frequency, the colloidal color is affected by electron density and charge distribution in the nanoparticles. So this is something that we saw in the bulk case also. But here when you have the size and it is the surroundings. So the role of surroundings is important here. So the dielectric constant function of the metal nanoparticle is size dependent. So this is epsilon, the dielectric constant. It depends on lambda and r. For different values of wavelength and different values of radius, the dielectric constant of metal will also keep on changing. So then we are able to utilize them for different types of, by tuning it to the near IR region, it is possible to have a very high, substantially high, this heat photothermal effect. And due to the substantial heat that is produced, they get killed. So this is the window that I was talking about, biologically transparent window, and there is a effort to tune this SPR peak, SPR frequency, SPR wavelength into this wavelength region, 650 to 1200, because in this region you can see the hemoglobin, melanin, these are the components, water. So beyond 1400 nanometers, you will see the water starts absorbing. 1400 nanometers, it is the absorption of water. Okay, of water starts 1400 nanometer and beyond, and below this range 600 something, you see that there is substantial absorption of blood, hemoglobin, oxyhemoglobin, deoxyhemoglobin. Then melanin has a significant absorption beyond this point. Melanin is a component that gives you skin color. Okay, so substantial absorption. So you have absorption by uh, HB, HbO2, O2, and melanin. You can see this. So it is the only this window which is available to us where the absorption is very very low for the biological components that we are talking about. And so laser irradiation of this particular wavelength will have no unwanted damage to the healthy cells. Okay, and when only the cancer cells where the nanoparticles are localized, they will have experience intense heat. So these are the things that has been, so this is, that's it. I have covered all these aspects of how the plasmon wavelength depends on different types of size. It depends on size, shape, internal structure. It also depends on the medium, and so the equation that came into picture. So you have all the things, all the aspects have been covered, and that's all for your this segment, nanomaterials, plasmonic. There's one more nanomaterial macromolecules which is falls in the regime of nanomaterial that we can discuss. That is dendrimer, and we will discuss in the next class. Tomorrow's class we will discuss the dendrimers. Okay, thank you.